Hey folks, welcome back for part 3. We're barreling through ionic compounds here. Okay, so we left off with this periodic table showing the common charges by group on the elements. This one shows the specific charges on the ions, and this one shows just the general trends going down the groups. With that in mind, here's a question. What ions are formed when magnesium transfers electrons to chlorine? Well, if you don't have the periodic table fully memorized, and you don't need to. You might need to look this up. Right, so you look up magnesium, and it's in group 2A. It's in period 3, row 3, but for this problem, that doesn't really matter. What matters is the group, right? So it's in 2A, and chlorine is a halogen. You'd find that in group 7A. All right, magnesium is off to the left of the periodic table. It's a metal. Metals lose valence electrons, form cations, and we know this one is not right. Yeah? Chlorine will not have a positive charge. So now it's just left to determine what the positive charge on magnesium will be and what the negative charge on chlorine will be. And magnesium is group 2A, so it has 2 valence electrons. It will lose those 2 and make a 2 plus charge. Excuse me. Chlorine has 7 valence electrons. It will gain 1, and so it'll have a -1 charge. And so this is the correct answer. Mg2 plus and Cl minus. Now on your own, what ions are formed when cesium transfers electrons to bromine? Okay, go ahead and pause this and try to answer for yourself. Welcome back. Cesium is Cs. It's in group 1A, so it will take a +1 charge when it loses that electron. It will transfer it to bromine, which is in 7A. 7 minus 8 would be a minus charge, so we get Cs plus and Br minus. Okay, third question. Why do ionic compounds form? So we went through what are ions, why do ions form, why do ionic compounds form? Well, one thing is the conservation of electrons is a new law that I just made up. But basically it says that electrons have to go somewhere, right? So if a metal is going to lose the electrons, there has to be a non-metal around to take those electrons. And so and vice versa, right? If a non-metal is going to gain electrons, they had to come from somewhere. So there has to be a metal or something there to give them up. So you could think about metals and nonmetals as they team up in ionic compounds. And the reason they do so is to become more stable. In the picture here is sodium metal, highly flammable, chlorine gas, which is actually Cl2, highly toxic, and put them together and you get table salt. So the answer to the question is they form to lower energy and increase stability. Now, I said they form. How do they form and in what ratios? So this is the formula unit tells us the lowest whole number ratio of ions that gives an electrically neutral ion compound and is determined by subscripts. When we write these out, we always put the cation first, followed by the anion. So the metal first, followed by the non-metal, which is kind of like left to right across the periodic table, right? So you can think of it that way. So for example, when magnesium and chlorine form ionic compound, you get MgCl2. So the little subscript down here means two chlorine ions. So we have one magnesium ion and two chlorine ions. Because the magnesium is 2A, it'll take a +2. Cl is a minus charge. And so if we have a +2 and -1 times 2, it's neutral. Okay, the middle one, K2O, potassium and oxygen. So this has two potassium ions, one oxygen ion, K is +1, oxygen is -2. So we have a +1 charge times 2 plus a -2 charge times 1 equals 0. If we look at the next one, Na2S, K and Na are in the same group. O and S are in the same group. And we see how we put together, we get 2 and 1, 2 and 1. Right, so two sodium ions, one sulfur ion, and the overall charge is 0. Okay, so another way that you can think about this is a nice little trick. So once you write out the ions that you have, like Mg2 plus and Cl minus, we can put them in order and we bring down the opposite. The charge becomes the subscript on the opposite one. So the one subscript 1 goes away and we get MgCl2. If we go here to K plus and O2 minus, the 2 goes here and the 1 goes here. All right, so that's a nice little trick. Bring down the opposite charges to become subscripts. And we'll do more practice with these, I promise. Okay, now how do we talk about these? We want to be able to talk about these things, communicate clearly, right? We're always thinking about communicating, and we want to be able to name ionic compounds. So there are some rules here, and we'll first look at the simple case. Let's say you have a main group metal and a main group nonmetal. So basically, kind of what we've done so far. So a main group cation just takes the same name as the element, but you say ion at the end, right? So calcium becomes calcium ion. Sodium becomes sodium ion. Great. Now anions, the nonmetals, the negative charges, they take on a different name. And you've probably heard this before. So you replace the ending of the element name with "ide," an ion. So like oxygen becomes oxide ion. Fluorine becomes fluoride ion. And here are those two examples so you can see how it looks. So we just take off the ending, replace it with "ide" ion. So then when we put them together, cations and anions, something like CaBr2 is just called calcium bromide. AlO3 is aluminum oxide, right? And there's only one way that they can be put together to be neutral, and so we don't need to say anything about the charges that's assumed. By the way, a little practice here, the aluminum oxide. Aluminum is in group 3A, so it takes what charge? 3 plus, right? Oxygen is in 6A, and it takes a minus 2 or 2 minus. So when we put them together, you want to swap down the numbers, and we get Al2O3. Okay, now if we have transition metals, right? Remember, some of these can take on multiple uh, charges. So a transition metal that exists in only one form, it's just like a main group. It just takes the same name as the element plus ion. Like Ag plus is just the silver ion. So AgBr is just silver bromide. But the transition metals that can take multiple forms, we have to use the parentheses and Roman numerals. Remember this from before. And then the word ion. So iron with a +2 charge becomes iron 2 ion. And then the ionic compound FeBr2 would be iron 2 bromide. And if iron takes on a +3 charge, it becomes the iron Roman numeral 3 ion. And then FeBr3 is iron 3 bromide. And you can see in these two cases why the Roman numerals are needed. Because if you just said iron bromide, we would not know which one we were talking about. So we always need to use Roman numerals if it has multiple possible charges. So if we go back to this page, we want to name these, right? Well, the first one would be what? Magnesium chloride. We don't need to say anything about the subscripts because there's only one way magnesium and chloride can be put together. The next one, potassium ion, and the oxide ion becomes potassium oxide. And the third one would be sodium sulfide. Okay, I think we'll stop here and we'll continue with another lecture looking at naming some more, and then we'll look at polyatomic ions. So this will wrap up lecture 3.1.